Good afternoon, everyone. Dr. Nat here. So this is replacement class for ECC 3129 that we didn't have last Tuesday. Excuse me. So I'm not going to turn on my camera today. I'm feeling a bit off. So hopefully everyone can still focus without seeing my beautiful face. Okay, so let's do a little recap. Okay, wait. All right. So what have we talked about last Wednesday? So this is recorded, so don't worry. And this is the last slide that will be on your quiz. So your quiz is on, let me write that down somewhere. Just a little recap for those who are sleepy or asleep during class last Wednesday. Quiz is Friday, next Friday. That is going to be 7 November. It's going to be from 3 to 4:30 p.m. Actually, it's just 1 hour, but this is like, what do you call it? Masa kecederaan. What is masa kecederaan in English? Emergency time. So that's 30 minutes. If something bad happens, there's an emergency. So that's the allocation that I have for you. Okay, so 3 to 4 is actually the time. We can extend it up to 4:30 depending on how the situation is. Okay, so this will be covering slide week 1 up until week 3. Okay, so week 4 is not going to be included, but it doesn't mean that you don't have to study for it because you will have your test in week 7. Okay, why is my handwriting so bad? Okay, test in week 7. Let me write that down here. Okay, week 7 is going to be on Tuesday. Okay, so I think that would be 2nd December. Good. Let me check. Tuesday. So that is going to be on 2nd December. Okay, and it is going to be from 11 a.m. until 1 p.m. And this will cover everything from week 1 up until whatever that we covered before the test. Okay, everything. Okay, so this is just like a heads up. I will talk more about tests later on. Okay, what you need to remember is we have quiz next Friday, and because of that, I decided to drop our class for Wednesday so that you don't have, I don't have the time. I don't have the rights to, have more classes than what is in the schedule. So if we are doing the quiz on Friday, so I will drop class on Wednesday. Okay, so that is all. Okay, let's continue. We need to do a little recap so that we are up to speed. So we talked about amplitude modulation. I'm going to make this a little bit bigger. Okay. And then we talked about sidebands. We talked about this in length. If your modulating signal is not a single frequency, it is a bunch of frequencies from 3, in this case is from 300 to 3000. So you will get a range for your upper sideband and lower sideband. Okay, and then we also talked about digital AM modulation, and we saw that there is 2 domains. One is called the time domain and the other is called the frequency domain. So usually our analysis will be done in frequency because it is easier to see where the signal frequency is, where the upper sideband is, where the carrier is. You cannot see where the carrier is here, you cannot see where the upper sideband here is. So this is good. The shape is nice. It tells us that this is an AM signal, but it doesn't give us a lot of information compared to when we work in the frequency domain. So time is important. The shape is important in time domain, but in frequency is where we get our calculations done. Okay. And then we talked about amplitude shift keying. Digital signals such as square waves can also modulate a carrier that is made up of sine waves. I'm recording, right? Let me see. I am recording. I am recording. Am I? Wait. Manage recording. Oh, I am. Okay. And then even though it is a digital modulating signal, you still get your M, the modulation index. Okay, can be 50, can be 100, it can be an 80%, etc. Then we talked about on-off keying, and then we talked about over-modulation, what happens to your AM signal. So instead of getting lower sideband, upper sideband, and your carrier, and we have these three sticks that we love, we get a bunch of sticks, which is caused by the harmonics. Harmonics is a type of nonlinearity that happens. Sometimes devices that we put in the circuit induces nonlinearity. Sometimes we can control it, sometimes we can't. So when this happens, if you still want to make this very optimized, you can make a band pass filter. We'll talk more about this later. Band pass filter. I think you talked about this in signal class as well, but we will talk more on this. And now we talked about this equation, PT equals to carrier power plus power of sidebands. So since we know that USB and LSB is equal, so this will become 2PSB. And then we did a bunch of derivations. Well, not really, it's not that hard. We know that we need to convert this to RMS first, and then we need to convert this. Okay, we convert it to RMS, which means that it needs to be divided by square root of 2, and then we need to convert this to PT, which means that this is going to be V squared over R. So V RMS squared over R becomes like this, and then we got a bunch of different equations from that as well. Okay. And then we saw that the total transmitted power is dependent on M, modulation index, and is dependent on carrier power. So the higher your modulation index, the higher your transmitting power is. Okay, and then we did a bunch of examples. I hope everyone understood what happened last class. Okay, so we did this, I think we did this already. So we are going to start here. Okay, so that was your recap. Hopefully everyone is up to speed. So we have another example on AM power. An antenna has an impedance of 40 ohms. We're talking about an antenna. Excuse me. So this R is 40 ohms. An unmodulated AM signal. What does unmodulated mean? So usually students, like in the quiz or in the test, they like forget. What is unmodulated, doctor? Well, unmodulated is signal that is not modulated, which means that it is still in its carrier form. Okay, please take note on this. Unmodulated means that it has not gone through the AM process, which means that it is still the carrier. Why is it not called the modulating signal? Why is it not called the message? If it is a message, it is going to be called a message signal or a modulating signal or an intelligent signal. Intelligence, because you are transmitting intelligence over the medium. So this is FM. This is going to be FC. Anything that says unmodulated is for sure carrier. Okay, even though it says AM signal, that's just to confuse you. Okay, because we love to confuse people. I don't know why. Okay, so this is FC. So FC signal produces a current of, so this is going to be IC, 4.8 amperes. The modulation is 90%. So M is 0.9. Calculate the carrier power. So carrier power, what is carrier C? And power is P. So that is going to be PC. This is what A wants. And B, the total power, it wants PT. The sideband power, it wants PSB. Okay, so let's find out. So how do we do this question? Anyone wants to give an idea? I'll let you guys give me some ideas. I'm gonna sip on my coffee and wait. Okay, any ideas? How should we do this? No one has any idea? Or you're just sleepy? Okay. This is... Okay, what is the equation for power? Yeah. Okay.
Doctor,
Yeah.
can we use P equals to I square times R?
Yes. Exactly that. Let's do that. Thank you, Sri. Okay, so PC equals to Sri said I squared R. Betul? For if we use voltage, it's going to be P equals to V squared over R, right? So this is the equation for I. Okay. So Sri said I squared R. So let's find out. We have IC. So let's put IC here. 4.8 squared times with R, 40 ohms. So that is going to be your answer. Okay, so it's going to be 921.6 watts. Okay, moving on. Next one. So we have PC. How should we get our PT? Do we have M here? We do. We have M. So we can use an equation that we have learned before. I don't know why my voice is like this right now. Not this one. This one. Okay, so we have PC already at this point. We have M, so we can find PT. So let's do that. So PT is equals to PC 1 plus M squared over 2. Okay, 921.6. 1 plus 0.9 squared over 2. That is going to be, where did I do it? Okay, PT is 1294. Oh, we have this answer already. 85 watt. Okay. And then for PSB, we have PT, we have PC. At this point, if you don't know how to do it, I don't know what to say anymore. Because at this point, it's pretty easy because it's just a simple equation. So PT is equal to PC plus 2PSB. Okay, so from here, PT is, let's rearrange this. So PSB is equal to PT minus PC divided by 2. So that is going to be 1294.85 minus 921.6 divided by 2. So you will get your power for the side bands, which is 186.62. Is there another way to do this? Yes, for sure there is. We have another equation for PSB. Okay, let me do this in a different color. So there is another equation for PSB. If you don't remember, I am reminding you, this is the equation. PSB is equal to M squared over 4 times with PC. We do have M, we do have PC. Already forgot what it is. Okay, M squared over 4 times PC. Okay, so this is going to be 0.9 squared by 4. And then PC is 921.6. Okay, so if you ask me which equation should I use, which is the best to use? My answer would be anything that does not rely on your previous answer. For example, you do PT and you mess up this answer, you get 1500 watt. If you use this equation, you're just going to make another mistake, right? Because PT is already wrong. Okay, assuming PC is correct. but your final answer for PSB is going to be wrong. But if you use this equation, you are only dependent on PC, which is the answer from here. M is given from your question. So this is like the safest route. So if I were you, I would double check using different equations if you have the time. But ultimately, don't make a mistake when you do the calculation, double check always. And if your answer depends on a previous answer, you need to really check. Okay. All right, moving on. So let's talk about antennas. We had like an intro to antennas, but not really. It was like just, hey, we have an antenna, find out what it is. Okay. So antennas in the real world, it is difficult to determine AM power by measuring the output voltage and calculating the power with the expression P equals to V squared R. However, it is very easy to measure the current in the load. So when we talk about circuits, we are usually measuring the current, right? We are like putting our ammeters and then finding out, oh, okay, we have a current of something, and then we times it with the resistance to find out the voltage. So that was the practice, I believe, when you were in your first year in circuit analysis. Okay, so for example, you can use the RF emitter connected in series with an antenna, same case like your circuits in first year, to observe antenna current. When the antenna impedance is known, the output power is easily calculated using this formula. And then one way to find the percentage of modulation is to measure both the modulated and unmodulated antenna currents. So before it is modulated, you measure it, and the output is, before you send it over, it is unmodulated. Okay, this is before the device, and this is after the device. Okay, remember we have like these inputs to a nonlinear device that gives us our AM signal. So you measure these things. This is going to be your unmodulated. I don't know which one, but one of it is going to be your carrier. And then your AM signal is your final modulated signal. Okay, so when you have that values, your IT is here. This is going to be your IC. You have IT, you have IC, you can find out what M is. So this is the real scenario situation lah. And we have an equation for that as well. Okay, let's do an AM power. The transmitter example, the transmitter of the previous discussed antenna experiences an antenna current change from 4.8 amperes unmodulated to 5.1 amperes. So right off the bat, we know that this guy is our IC and this is going to be our IT. So even if you didn't understand this question, your IT needs to be bigger than your, wait, is that always the case? Your PT needs to be bigger, but if your R, okay, so I cannot generalize like that. So it says here unmodulated, so that's going to be your IC. So what is the percentage of modulation? So back to the equation over here. We have the equation, we just need to use it. M equals to square root of 2, and then IT over IC squared. Can't really remember this one, so let me just copy it. Okay. So I have a cheat sheet over here. And then I'm going to get a question from you guys in your head. Are we allowed to bring our cheat sheets? No, the answer is no, but I will give you equations in the quiz. So hopefully that answers some inside thoughts. Okay, so let's use this. M equals to 2, IT is 5.1, then we have our IC is 4.8, then we have this. Okay, I'm not using this correctly, -1. And then this is squared. See, it is complicated, isn't it? It's, this is 2, and then we have a bracket, and then we have a squared. So make sure you don't use this incorrectly, okay? So whatever that is, that's the answer. And then this will give you your modulation index, times it with 100%. You will get your modulation percentage. Okay. Okay, any questions so far? Everyone is still with me
Tak
on
ada.
this lovely Friday evening? Yes. Do, does anyone
Tengah
have questions?
tengah salin.
Oh, apa Syafiq tak dengar?
Tengah salin.
Tengah salin. Okay, go ahead. Okay, dah salin ke?
Uh, boleh lah. Dah.
Okay, moving on. We will have our break at 3:40. Another 20 minutes. Bear with me.
Jawapannya apa?
Tak ada. I don't have the answer.
Okay.
Okay, so moving on, we talked about powers, and that is the chapter on powers lah. Now we are going to be introduced to a different world than AM signal. Okay, so some of you are going to panic, some of you are going to be curious. So hopefully I can take everyone to be curious after this. So we have a new name to understand. It is called DSB or DSSC. Let's just use DSB to make our lives easier. It is called double sideband, or if it says DSSE, double sideband suppressed carrier. We have it here, or we do. Double sideband suppressed carrier, or DSP. Double sideband. So when we say double sideband, it is understood, okay, there's no carrier in this signal. There's only a double sideband. What does that mean? Okay, so our regular AM signal looks like this. FUSB, FLSB. The carrier is gone. No more. What's that in Spanish? I don't know. What is no more in Spanish? I haven't learned that. Okay, what is no more in Chinese? Anyone? What is no more in Chinese? Come on, Chinese people in my class. I'm gonna ask Sri for the Indian version. There's no equivalent for no more? Or are you guys sleeping? Okay, for Malay, it's called tak ada lah. Tak ada. So this is Malay. Okay, this is no more. Okay, what's the equivalent for Isri speaks in Hindi or Tamil?
Tamil.
Okay, what's Tamil equivalent for that?
Illai.
Ile.
Mm.
Like that?
Ends with an I,
Ends with an
No.
I. Okay.
not a K. I.
Ile. Okay.
Mm.
What's the equivalent in Mandarin? Or Hokkien?
In Mandarin, it's called 没有了.
Oh, mayo. Like this?
Yes.
Oh, okay. Okay, so we have mayo and ile. So I'm going to use that. Cool. Okay, so your FC is now ile. No more. Okay, so that is your double sideband. So the real information is contained in the sidebands because that is where FM is. So it's not a big problem even if we don't have FC. Because remember, our FLSB is FM plus FC. Terbalik. Sorry, this is not that. Oh no. Excuse me, you need to be erased. So this is going to be FC minus FM, and this is FC plus FM. So we still have our FC, we still have our FM in here, even though our FC has been mayo, okay, if I'm using that correctly. Okay, so we can improve the efficiency of AM by suppressing the carrier. So this is actually towards optimization of bandwidth and towards optimization of power. So we suppress the carrier, and then we can also eliminate one sideband because why? The information is already inside one sideband. So even if I get rid of this, I still have FC, I still have FM, even though it's a combination. Okay. So in AM, 2/3 of the transmitted power is in the carrier. Is this correct? We will find out. Which carries no information. Remember, our carrier does not carry information. it doesn't have information, but it carries our information. Remember, our FC is like a horse, and the FM is you. It's not me, it's you. So you are on this horse. Oh, this is a very bad horse. And you are being transported from A to B. So you are the information. This horse, I mean, we can get rid of it. You can still walk, right? So as long as you reach destination B, it's already good. You can walk, that's your form of transportation. Sometimes you use the bicycle, but the horse is maybe the efficient way to transport it. Sometimes we don't want it because it uses a lot of money. We need to buy the horse. Okay, so we get rid of it. Okay, so again, double sideband is towards power optimization by suppressing the carrier. So we don't have to put power in transmitting the carrier. And we can also eliminate one sideband. And this is not DSB. We will talk about this part later. So double sideband suppresses the carrier, which means that the power to transmit is now less. Okay, so how does it look like? Okay, so our AM signal is like this. Okay, remember? That. And this is our reference 0. Okay, assuming the modulation is not 100%. So it is not going all the way. So if it is 100%, then it would look like this, right? Okay, a little bit closer because it's 100%. Okay, so how is it different from DSB? It looks similar, right? You can see this. You can see that there is some points that looks like AM signal when it is 100%. Okay, let me clarify this, the difference to you. So here, what's happening here is it's not doing this. It's not doing this. It's not, how do I say this? It's not being mirrored like AM. AM, we have the mirror going on, right? It reflects. It's going to give us a symmetrical shape. In this case, for DSB, what happens is that when it goes positive and then it intersects the 0, and then it says, okay, goodbye, I'm not going to continue this journey. I'm going to continue being positive. So it stays positive all the way. It stays positive all the way. And then you get the mirror like this. Okay, how is it different? We don't have this. It's not allergic to 0 in AM signal. For AM signal, it's not allergic to 0. It means that even if we overmodulate, it can still go down, right? So what you will get an error, which we don't want. But meaning to say, the 0 is not its limiting factor. This reference 0 is not a limiting factor to a regular AM signal. But for a DSB, the 0 is like haram lah. How do you say this? The 0 is like, what's haram for you guys? If you go through this, you will sin. if that's an easy way to. Oh, kesiannya, okay, we have a person named Sin. Okay, I'm not going to use sin. Dosa lah, dosa. Kesian Sin, terbabit pula. Dosa. I think Sin understand what dosa is. So if you cross the 0 barrier, you will be berdosa because it's haram. So this DSB is like that. Okay, let's talk more about it, and hopefully I don't melalut so much. Okay, why do we suppress the carrier? Because a unique characteristic of the DSB signal is the phase transition that occurs at the lower amplitude portions of the wave. So what I explained to you, that I said that, okay, we cannot pass this barrier, the 0 barrier, is called phase transition. When it goes to the 0, it's going to be phase transition, and the phase transition. So that is what's happening. The phase transitions occur at the low amplitude portions of the wave. So this is the low amplitude portions. In the figure, note that there are 2 adjacent positive going half cycles. Okay, 2 adjacent positive going half cycles positive cycles, this is what it means, at the null points in the wave. Okay, so it's saying, okay, like that, adjacent positive, adjacent at the null points. Null points is 0. This indicates true DSB signal. So in week 5, I think, in week 5, you will see the difference between AM and DSB. Memang, this is exactly what you will see. The positive half cycle that is adjacent at the null points. DSB are generated by a balanced modulator circuit. We'll talk more about this later. And or a product modulator. DSB AM saves significant power, as I mentioned to you before. So if you see this kind of figure, there is a dash here. It means that it's not there, but you just draw it to say that, okay, this is where the original carrier is. So let's just put a dash there. This is a solid line, means that it's there. Okay, dash means skull or a potato. Okay, moving on, we talked about DSB and we found out that DSB saves us power. This is how it looks like. Now let's talk about SSB, single sideband signals. Okay, as the name suggests, we only have one sideband. Previously, we had double sideband. In this case, we have one sideband. Let's get rid of this. This is going to be Mayo lower sideband. Okay, LSB is no more. So we are left with this guy. So the benefits are the spectrum space occupies only 1/2 of AM and DSB signals because you only need to transmit this portion. So the bandwidth is lower. This is towards optimization. This greatly conserves spectrum space and allows more signal to be transmitted in the same frequency range. What this means is that previously you used 10 watt to transmit this guy, right? And then maybe you used 8 watts to transmit double sideband. For single sideband, even if you use 8 watt, this upper sideband is going to be like so big that the signal is so strong and you are not going to be having issues demodulating this signal later. So even if you use the similar power, the signal strength is phenomenal. It's great. So sometimes we need that. Okay, because SSB occupies a narrower bandwidth, the amount of noise in the signal is reduced. There is less selective fading of an SSB signal over long distances. Okay. Right. So in SSB, when no information or modulating signal is present, okay, what does this mean? This means that when we are not talking on the phone, it doesn't transmit anything. When there is no voice, there is no modulating signal, you don't need to transmit the FC, right? In SSB, so there is nothing, basically nothing, because FM is not there. You don't have to transmit FC. But for AM signal, okay, let's draw this nicely. We have signal, we have our voice signal. What's going on with my eraser? Don't know. Let's do two scenarios. One is we are talking. Okay, one is we are talking. Number 2 is we are not talking. Because I'm fighting with you. Okay. So we are talking. In a regular AM, what happens? I need to transmit like this. I will have FM here, FC minus FM, and FC plus FM here, and FC, regular signal. We are talking, obviously this is going to be a range, right? Okay, but we are simplifying this scenario. We are talking, I'm transmitting this. If in SSB, if we are talking, I am transmitting this. This is not there, this is not there. So it's FC plus FM. This is what I'm transmitting. We are not talking in AM. I am transmitting FC. Regardless if there is no information, I still need to transmit my horse. I still need to transmit my carrier. But for SSB, when we are not talking, Nothing. Nothing is being transmitted. Is that a good thing? Yes, because we don't waste power unnecessarily, we don't waste bandwidth unnecessarily. So if you're paying your bills yourself, your bill is going to be less. Okay, to put it simply. Okay, so in SSB, when no information or modulating signal is present, no RF signal is transmitted. In standard AM transmitter, the carrier is still being transmitted even though it may not be modulated. In SSB, the sidebands are generated only during modulation. So let's say you're not talking, there's no modulating signal, so nothing is going to be transmitted at all. So this makes SSB more efficient than AM. Okay, so let's take our break now. Let's take our break for 7 minutes. Let's come back at 3:45 p.m. You can ask any questions if you have any. Okay, everyone, let's continue. So let's talk a bit more on DSB and how the shape is different than a 100% modulated signal, a regular AM 100% modulated signal. So if you can see over here, oops, okay, this part. So at lower amplitudes, okay, it's not going through a phase transition. So bear with me. I know like phase transition, the term phase transition is throwing you a bit off. So if you look over here at lower amplitudes, it keeps going, even though it's like zero. It's like very small. It keeps going. Okay, it keeps going. But here, it doesn't keep going. If once the positive half cycle ends, it flips. Okay, you can see the inside. Let me use a different color. You can see the inside, it flips. It flips like that. So instead of going and then like that, macam tu. Dia macam flip. So this is DSB. It doesn't go all the way to zero, it flips when the positive half cycle ends at zero. Okay, I know that is like not really obvious. It's not really obvious. Okay, so but if you see something like this, that it is like almost like 80% true that it is a DSB signal. Okay, unless it says, okay, so this is a 100% modulated signal, then you need to like worry, okay, is this a DSB or is it like 100% modulated AM signal? Okay, so but generally this is how it looks like. Okay, so what does it mean by flip? Okay, when it flips, it goes 180 degrees phase transition. So the book doesn't introduce this term yet because it's a bit confusing. But what happens is that the phase transition is actually 180 phase transition. So 180 means you're flipping, right? 180, yeah. So if you are over here, 180 degrees flip would land you down here. So basically flip lah. Flip. So this is what's happening. 180 degrees flip. From here, like that. Okay? So don't stress yourself over this phase transition. I want you to understand this shape. This shape looks like this. There is a phase transition at the 0 point, and that is the characteristic of a DSB signal. Okay. Okay, moving on. So we talked about how DSB is good. It saves us power. Then we talked about SSB. It is even way better than DSB in the sense that, okay, the power is good and then the bandwidth is also better. So, but of course, with good things, there's always like a catch, right? As everything in life, nothing can be too good. There's always a catch. So maybe that is a pessimistic thinking. But as engineers, you need to be wary if something is too good to be true. Okay, so there are obviously disadvantages of DSB and SSB. It is difficult to recover or demodulate. Transmitting is very good. Transmitting, you reduce bandwidth, you reduce power. It's very good. It's excellent. But when it is time to demodulate it or to decode the signal back to the voice so that your friend can hear what you're talking about, it is difficult. Because why? Because the carrier is not there. The carrier is not there. I told you that the FC and FM is part of the signal, right? But it's not on its own. You have to do some filtering to get out the FC, right? So that is the hard part, to recover the signal. Demodulation typically depends on the carrier. If no carrier is present, then it needs to be regenerated. Because again, it's tied together with FM. It needs to be regenerated at the receiver and reinserted into the signal. The reinserted carrier needs to have the same phase and frequency as that of the original carrier. Okay, so that is the disadvantage. There's no carrier, therefore it is difficult to demodulate. To overcome this, a low-level carrier signal is transmitted along with two sidebands in DSB or a single sideband in SSB. What does that look like? So this is our DSB, and the other side is saying, hey, give us like a pilot carrier, or a small signal carrier, so that we know what we're working with. So we give them like this tiny thing. So that's your pilot carrier. It gives us the FC, but it doesn't use as much power as a regular carrier. Because the carrier has low power level, the essential benefits of SSB are retained, but a weak carrier is received so that it can be amplified and reinserted. So at the receiver side, they will need to amplify the FC and do whatever things that they need to do to get out the FM. Such a low-level carrier is referred to as the pilot carrier. So it's not a regular carrier. If it's low level, just to help SSB and DSB, it's called a pilot carrier. So that's the term that we need to remember. Okay, moving on. So in standard AM, the power is distributed among carrier and two sidebands. So remember, we have this. The total is PT, and PT is distributed over here. This is PC plus PSB. We talked about this. Sorry, it's 2 PSB. So PT is distributed among PC and 2 PSB. For example, a 400 watt carrier with 100% modulation will have sidebands of each 100 watt. Therefore, the total power transmitted is 600. Let's try this. So PT is what? PC 1 plus M squared over 2. So we have our M, we have our PC, which is 400. 1 plus 1 over 2 is 1.5. Therefore, it is 600. So that is how it was calculated. The effective transmission power is the power in the sidebands. Effective transmission power is the power in the sidebands. Because why? Because that is where the message lies. So PC is 400, right? Let me write this over here. I don't know what's going on with my eraser. Okay, working. Okay, so this is 400 watt, this is 100, and this is 100. So effective transmission power is these two guys because they carry FM. So that makes it 200 watt. An SSB transmitter sends no carrier but will have some communication effectiveness as standard AM running at more power. So if you use 40 watt of power in standard AM, it splits like this. 30 watt is wasted on the carrier. Okay, so it's 30 watt. And then 10 watt is used for the actual sidebands. 5 watt. So this is not 100% modulation. I believe this is 80%, but it doesn't really matter. We're just talking about the sidebands is using 10 watt and the PC is using 30 watt, and the ratio is not correct here. Let me redraw this. Very small. 5 watt, 5 watt, 30 watt. Okay, so to achieve the same strength as a standard AM, the SSB should transmit 10 watt. Okay, so this is regular AM, this is SSB. Now, if we are transmitting single sideband, the confusion will be like this. I want to transmit a single sideband, therefore I only need to transmit 5 watt because it's a single sideband, right? But in this case, the effective transmission is 10 watt, meaning to say when this reaches the user or the receiver, what they're getting is 10 watt of FC plus 10 watt of sidebands. SB, 10 watt of SB, which is the FUSB plus FLSB. 10 watt of SB. and that is the strength that they get. So in the SB, there is FM, so that is the strength that they get, just 10 watt. But if you transmit SSB, just taking this guy, this is going to be 5 watt of strength. It's not going to be the same. So if you say SSB is better than the regular AM signal, the user will disagree. Because why? Because what they're hearing is my voice being lowered. Yes, the signal is transmitted, but my voice is now not the best. You're hearing this at low volume, for example. So to achieve the same greatness but at an effective power transmission, we will need to transmit our SSB signal at 10 watt so that the strength remains the same and we retain all the benefits of using SSB. So this needs to be 10 watt of USB. Does that make sense? Everyone okay? Still okay? Tak faham? Faham? Tak faham? Faham. Okay, Terry said thumbs up. Okay, thank you, Terry. Thank you, Akil. Okay, to achieve the same strength, again, to summarize, to achieve the same strength as a standard AM, the SSB should transmit 10 watt. So this is not to be confused as taking the SSB from a regular AM, because we're not working with regular AM. We are making our own SSB, and to achieve the same strength, we need to have 2 SB equivalent of AM signal. So the SSB transmitter needs to transmit 10 watt total to sound as strong as a 40 watt AM transmitter. We are still winning, but we are winning effectively, giving it a 4-to-1 power advantage. So this is what we want in life, effective transmission. Right, moving on. Let's talk about signal power considerations. In SSB, the transmitter output is expressed in terms of peak envelope power, PEP. So we have our VRMS, peak to peak square root job. Is this correct? I need to double check this equation. Okay, let me double check this one. Okay, let's see. For example, assume that a voice signal produces 360 volt peak to peak signal. Okay, we talked about peak to peak versus regular peak. Remember what it was? So peak to peak is all the way from up to bottom. But if we're just talking about peak, why did I use a similar color? If we're talking peak to peak, it's from goes all the way. But if we're talking about just the peak, this is what we're dealing with. Okay, the black guy is peak to peak, peak to peak, macam ni. And then this is just peak, peak to peak, PP, or voltage, can be the same. Okay, so the RMS voltage is 0.707 times the peak value, not the peak to peak value, and the peak value is 1/2 or 0.5 of the peak to peak voltage. So if your peak to peak is 360, your V peak is 360 divided by 2. Okay, and your VRMS will be your V peak divided by square root of 2. So this is what's happening here. 360 divided by 2 square root. I need to double check. Is it divide by square root of 2 or times square root? This I don't remember. Okay, and then we divide by 50. Where is 50? 50 is your R. So because it's power, this is going to be squared. Okay, remember we have VRMS squared divided by R. This gives us our PEP, peak envelope power. Okay, so then there's going to be a question like this, because you're not going to ask me, Doctor, why do we need PEP? Why don't we just use PT? Okay, because this is like this is specifically for SSB. We have PT for our regular AM signal, right? PT is PC plus P2 PSB, that's your AM signal. In SSB, because you're transmitting a little bit different than a regular AM signal. Remember what we talked about just now, like 5 minutes ago? This is regular AM. This is SSB. It's amplifying the upper sideband, so it doesn't follow the conventional AM. So you need to like explain this, no, explain. You need to calculate this differently. So this is how they calculate it differently using PEP. They just want to do it like that. Okay, and then moving on. Okay. Question, an SSB transmitter produces a peak-to-peak voltage of 178 volts. Okay, this is peak-to-peak across a 75 ohm antenna load. What is PEP? Okay, so this is VP to peak, 178 volts. The R is 75 ohm. PEP is easy. It's just plugging in the equation of 178 divided by 2 to get the peak value, and then square root to get the RMS. You need to double check this one, and then you square this because it's VRMS squared divided by R to get the power. Okay, so there's going to be something. Let me double check on the VRMS. I am confused a bit, but I think you can understand if we have a certain equation for VRMS, right? It's going to be times with 0.707. So that is for sure. Let's just use that instead. 178 times 0.707. This will give us our VRMS squared. Okay, this is confirm betul. Okay, so that's the answer. Whoopsie, what happened? Okay, bear with me. Don't sleep yet. Okay, so the PEP input power is simply the DC input of the transmitter's final amplifier stage. Okay, so remember we have like our transmitting thing going on in week 1. We talked about gain. And then we have our amplifiers. Some were arranged this way. And then we had a circuit whereby we had like a bunch of circuit, and then suddenly there's an amplifier to amplify the signal to get our output good. Okay, so this is what it means. You have your circuit. At the final stage of this circuit, you have a final amplifier stage. Don't really have to care what this is. You just need to know, okay, this is the final amplifier stage. This is what this question is saying. At the instant of the voice envelope peak, the PEP input power is simply the DC input power of the transmitter's final amplifier stage. So you have your DC input power here. This is what PEP is. DC input power stage at the instant of the voice envelope peak. So DC input, okay, at the maximum. This is your voice is like that. And then where does the maximum happen? This is where the DC is being transmitted at the maximum peak of your modulating signal. Okay. And then it is the final amplifier stage DC supply voltage multiplied by the maximum amplifier current that occurs at the peak. So this is the current max. So we have DC input power and I max happening at the same time to produce PEP. So this is V supply to the amplifier, VS. Okay, V supply, I max. The current when your voice is at the maximum peak. So you will get PEP. So there are two equations for PEP for SSB. PEP is specifically for SSB. This is the second equation. The first equation was VRMS squared over R. This is like the simplest one. It depends on the question. If they talk about the amplifier final stage, you will need to use the second equation. If they just give you the VRMS or the V peak to peak without saying the condition and they want you to calculate the PEP, then just use it as it is. Okay. Self-study. What are the uses of AM, DSB, and SSB? So please find out. And I'm going to put a section on Putra Blast for you to put in your answers. I think it's going to be like a forum. Okay, and I want everyone to answer this on Putra Blast later. I'll let you know when I put it up. What are the uses of AM, DSB, and SSB? Right. So that is the end of week 3 slides. I'm going to continue with week 4 because again, we don't have class on Wednesday, right? So we're going to go over on week 4 a bit. So I'm going to give everyone a 7-minute break first, and then we will continue up until maybe 4:50 or 4:45. Okay. 4:15, come back. We will continue until 4:45. Okay. Any questions? No questions? Okay, please take your break. I will be here if you have any questions.
Betul.
Yep.
Yang uses of AM, DSB dengan SSB tu, users tu maksudnya macam penggunaan dia ke, maksud dia ke,
Um,
anything about
anything je.
okay bang.
Okay, so let's continue. I am still recording. Okay, yes, I am. Right. Oops, lupa nak buat ni. Okay, so let's continue. So this is week 4 slides. I'm doing this today because we don't have class next Wednesday. So this is sort of like a replacement class a bit. We are still going to talk about amplitude modulation. What is there more to talk about this guy? A lot actually. So we are going to talk about the block diagram of a circuit to produce AM now. So we talked about the power considerations. We talked about how AM can be done as DSB, double sideband, by suppressing the carrier. We also talked about how we can actually conserve the bandwidth by using SSB. But for SSB, there is a special case whereby if we want the same effectiveness of a regular AM signal in terms of strength, therefore it cannot transmit the same the same power as a regular AM signal, but it needs to amplify it a bit so that the effective transmission is similar, but retain all the good stuff about SSB at the same time. Okay, so the power advantage was 4-1. We discussed this, and we also did some calculations. Well, the general calculation. And then we also found out that there is another term for power for SSB, which is called PEP. Okay, power envelope. What was it? PEP, peak power envelope. Peak envelope power. Peak envelope power. Or power envelope peak. I forgot. Okay, let me see. Open recent 3. It was called PEP, peak envelope power. Okay, peak envelope power. Right. Okay, so now we are going to talk about block diagram of a circuit to produce AM. Okay, recall our equation. VC sine 2 pi FCT. Okay, this was our FM signal. FC signal. And then this is our FM signal multiplied by our FC, but this guy doesn't have the peak voltage. This one has VC. This one doesn't have VC. Okay. So recall, this was what we talked about in week 2, I believe. And then we know that modulation index is basically VM over VC. And we can rewrite this in VM equals to MVC. So if I were to rewrite everything in terms of VC, I would substitute VM, right? VM as MVC. So what will happen is VC is retained. VC sine 2 pi FCT is retained. I'm trying to make everything in VC. So VM, I need to change it. So it's going to be MVC sine 2 pi FMT. So the FM doesn't change. Sine 2 pi FCT. So only this guy is changed. So now I can rewrite it like this. I'm going to extract VC sine 2 pi FC from this entire equation. So VC sine 2 pi FC. So this becomes 1. Sorry, this becomes 1. Wait. Yes, this becomes 1. VC and sine 2 pi FCT. Okay, we have this. So this is 1 plus M sine 2 pi FMT. Okay, so if this is not obvious to you, how should I do this? Okay, M sine 2 pi 2 pi FC No, I want to do this as F, M. Okay, I'm putting this next over to M, and then we have not anything else, just rearranging. This is FCT, is not a term. Okay, contoh. So I have this guy from here, so that becomes 1. Sorry, 1 is from here. So again. The 1 is from here, plus M. I think you got it. Okay, maybe everyone is. I'm just sleepy right now. Sorry. I don't know what I'm saying. Let me re-say this. Let me rephrase this. Okay, wake up, Nadia. Oh. Okay, sorry about that. Let me rephrase what I said so that it's not confusing. Okay, so we have VC sine 2 pi FCT, right? Okay, so this is our guy. We want to make it, we want this term. How do we get it? So I am taking this out, so this becomes 1. I am taking this out as well, so I can factor out VC sine 2 pi FCT from both of these terms. I'm factoring out VC to pi FCT. What I'm left with is, this is 1, because multiplying by the factor 1. This is plus, right? M, what's left is M sine 2 pi FMT. M sine 2 pi FMT. So this is how we get this equation, just factoring out, which should have been easy, but saya melalut tadi, sorry. So we also know that VC, instantaneous carrier voltage, is VC sine 2 pi FCT, right? So we can rewrite this as small VC. So with that said, this can be A, and it kind of looks like our equation for gain. So A times whatever is an amplification or a gain of something. And A can be any circuit. It can be an amplifying circuit, it can be a non-linear circuit, it can be an attenuating circuit. But for the case of AM, it is a non-linear circuit or a non-linear device that will give us the signal modulation. So signal modulation cannot happen if the circuit is linear, it needs to be non-linear. Okay, so now let's discuss about the circuit. This is how it looks like. We provide 2 inputs, our modulating signal, and this is our carrier signal. We multiply it, and then we add VC sine 2 pi FCT. This is summer. Multiplier is indicated by an X, like this. Okay, and summer is indicated by this summation symbol. Sum. Multiplier, multiply. So you are multiplying these two guys. So what happens is Vm sine 2 pi FMT. Okay, and then you multiply sine 2 pi FCT. Okay, looks familiar, right? And then we sum with this guy plus VC sine 2 pi FCT. Basically, what we saw just now, which was VAM, this was it. Then we factor out the VC sine 2 pi FCT, 1 plus M sine 2 pi FMT. Same thing. Except now this is a block diagram. So in this class, we will talk a lot about block diagrams. Okay, so multiplier, you just multiply it. Summer, you just add it together. Okay, so here is another version from the book. This is, remember I told you in week 1, I am actually referring all my content from a single textbook. Some links are used to enhance your understanding, but the book is where my syllabus comes from. Okay, modulating signal, which is your Vm sine 2 pi fmt, then your carrier, and then here they drew it like this. I separated them because this guy doesn't have VC, so I didn't like how they combined because it's going to be confusing. In this case, they combine, and assuming they have some filter over here to suppress the VC, so it's going to be sine 2 pi fct. And then finally, you get your VAM. This is from the book, and it is equivalent to what I drew over here. Okay, moving on. Block diagram of a circuit to produce AM. So we are still in the topic of block diagram. We discovered that VAM can be represented by this simplified equation, which is A times instantaneous voltage carrier. A times instantaneous voltage carrier. So if we were to represent it in like a very simplified block diagram, we already simplified it like this, right? This is even simpler. We have V, and then we have our A over here, and then finally we have AVC. V, after it passes through this amplifying gain, it becomes AVC. In this case, A is M sine 2 pi fmt plus 1. A is proportional or a function of this is like this. A is proportional or a function of M times sine plus 1. Okay, so A in this case is this guy. V is VC sine 2 pi fct. When you multiply with this gain, you get your AVC or your AM signal. Now this is if it is greater than 1. If we are working with VC and the gain is less than 1, we have talked about an attenuating circuit, which is the voltage divider, where A is equal to R2. This is AVC. Our output is here, and AVC in this case is going to be less than VC because this is a voltage divider. So A is presented by R2 over R1 plus R2. So this is still non-linear. This is still non-linear. So it still works, but it's not amplifying, it's attenuating. Okay, so A and B shows multiplying the carrier by a gain A. Okay, A, in this case, A is greater than 1. In this case, A is less than 1. If the gain of the amplifier or the attenuation of the voltage divider can be varied in accordance with the modulating signal plus 1, modulating signal plus 1, if the gain, if A from here or here can be varied in accordance with our voice plus 1, AM will be produced. Because it satisfies the condition that the device or the circuit needs to be non-linear. So it will work. As long as it can be varied, it follows our voice modulation, then it will be multiplied with the carrier and we will get our AM signal. Okay, so hopefully this concept doesn't really throws you off. It's the first of many circuits that you will see. Ta-da! Okay, moving on. So square law circuit for AM generation. So another way to generate the product of a carrier and modulating signal is to apply both signals to a nonlinear component. Again, the condition is for AM signal generation, you need to have a nonlinear device or a nonlinear circuit. If it is linear, it's not going to work. This is linear. Why is it linear? You increase one, you get an increase in one. Let's say A is a fixed value of 10. And you put in VC times A to get your output, right? So V out. So if VC is 1, and then this is 10. If VC is 2 times 10, this is 20. So this is linear, it's fixed. The gain is fixed. So this is 1, this is going to be 10. This is 2, this is going to be 20. This is 3, this is going to be 30. It's linear, proportionally increases. Sorry, linearly increases. The gradient is constant. That's a linear graph or a linear circuit. What we want is this guy, a non-linear behavior. So an example of linear components is your resistor, fixed value, doesn't really vary, or linearly biased transistors. Fixed values, you put in a fixed value inside a fixed device or a linear device, the output is very predictable. You already know what it's going to be. But for a non-linear device, you have to use the equation to find out what the output is. You can't really predict it unless you can predict equations in your head, but most of us can't. Okay, so examples of nonlinear components such as diodes, bipolar transistors, and FETs. So if you see this component in your circuit, you know that there is nonlinear equation happening, or something that is not linear lah. Okay, this is linear, this is non-linear. Okay. So this is a linear voltage current relationship, a non-linear or square law response. So another term here, square law. And people will say, oh, what is square law? Why do we have to know about square law? Square law is just, it simply means non-linear. Why is it called square law? Because a squared is nonlinear, a to the power of 3 is nonlinear, a to the power of 4 is nonlinear. Only a to the power of 1 or a to the power of 0 is linear, because it's basically linear graph, right? So if it's a squared, you won't get a straight line graph. If it's a to the power of 3, you won't get a straight line graph. If it's a to the power of 4, you won't get a straight line graph. That is what it means by nonlinear graph or nonlinear response. There is a power of something. So I believe this, you will use more of this in other classes as well. So when they talk about something that is non-linear in physics or in engineering, it always means that there is a power of 2 or more involved. Okay, so that's mathematically. Okay, so this is how the circuit looks like. Bear with me, we have another 15 minutes. Since transistors and diodes are not pure square law functions, okay, remember square law is just basically to the power of 2 of something, we get undesirable harmonics because they are not purely a to the power of 2. They are maybe a plus 1 plus 2b to the power of 2. Who knows? It depends on the circuit that we're designing. So it's not purely this, it is almost always like this. A bunch of things to the power of 2. Okay, so when it is not a pure square law function, we get undesirable harmonics. So we meet again harmonics, the undesirable nonlinearity, which can be easily filtered if necessary. So this is our VM, this is our VC. VM is our modulating signal, VC is our carrier FC. It passes through our diode. Remember, diode behaves like a square law response. It is a non-linear device. So therefore it is not predictable. Okay, so this is the input, this is summation. So at this point we have our V in entering the diode. The diode is our non-linear device. This is the diode. And passing through V in, passing through the diode will give us V out T. V out that is dependent on time. And it can be VAM if it is done correctly. So I'm not going to go over this. This is too much. Okay, let's ignore that. Do I want to do this? No, I don't want to. We will talk more on this when we talk about balanced circuit. So ignore slide 9. I'm going to hide this. And this. Everyone's like, oh, sebaik, no more derivations. There's more derivations later, but that's not important. Okay, so since transistors and diodes are not pure square law functions, we get undesirable harmonics. We talked about this earlier, and it can be easily filtered if we want to. So let's talk about how. These harmonics are also known as intermodulation product. We meet again, intermodulation product. Intermodulation product was introduced to you together with harmonics. Both are noise, undesirable. Okay. So this is a square law circuit for producing AM. This is the output. And because it is not a pure square law function, you have a bunch of harmonics and you want to get rid of it. So how do you get rid of it? Do you have the answer here? Yes, we do. So you use a band pass filter. Okay, so I don't know how much you know about band pass filter, but I'm going to explain it again. So band pass filter is a type of device. Okay, it's a type of device that limits the bandwidth that is passing through. Okay, so if we pass through V in or no, not V in. If we pass through V out, okay. V in after this is a V out, right? So I need to do this as V2 over here. Maybe V out version 2. Okay. V out is here. It has a bunch of harmonics. I don't want it. I want to pass this output V out T through band pass filter. So what happens is that it's going to limit the bandwidth. Limit the bandwidth. So let's say the band pass filter has a bandwidth of 2 FM and FM is equal to 100 Hertz. Therefore, the bandwidth for this band pass filter is 200 Hertz. Okay, so that explains one part, the bandwidth. But how do we make sure that the 200 Hertz is effectively getting this part? It can be also here, right? Because it's 200 Hertz. So how do you determine where the 200 Hertz is? Okay, so the answer is a band pass filter has this resonant component inside it. Resonant component. Okay. What does resonant mean? Resonant means that it follows a certain frequency. It follows a natural frequency or a certain frequency when we tune it to that frequency. So resonant component. So we will tune the band pass filter to have its resonant frequency at FC. Resonant frequency at FC. So when the resonant frequency or the operating frequency of the band pass filter is at FC, this is going to be the midpoint and this is going to be the 200 Hertz bandwidth. Let's say you messed up. You design a circuit, your resonant frequency is off. You put your resonant frequency at 2 FC. What will happen? Okay, you have your device. It's supposed to be good, but you messed up in terms of the resonant frequency. So your band pass filter is now going to allow only this portion to pass through. Because why? Because you set it to 2FC, which is wrong. So what happens? Your output will be, instead of FC, FC plus FM, FC minus FM, instead of the regular AM signal, what you will get is 2FC, 3FC, FC plus FM. Doesn't really look like an AM signal, right? So when you want to demodulate it, I will say good luck to you because it's going to be hard. Okay, but ultimately don't mess up. Okay, make sure your band pass filter resonant frequency is at the carrier frequency. Is that okay? Does everyone understand? Okay ke? Tidur ke? Everyone is confused at this point? A lot of crying. Okay. So I'm assuming crying and confused. How would that look like? Okay. Okay, so which part should I re-explain? Is it the band pass filter? Or which part? So do we understand what the square law response means? It basically means it's not linear, right? Okay, so square law response is okay. But the band pass filter, is that the part where you need more explanation? Guys, we are in electronic communication. Please use your voice as the modulating signal.
Ya, ya. Ya,
Betul? Okay.
lepas pada square law tu dia macam lost lah.
Okay. So I will repeat this one more time and then we will end class and hopefully we will we will let our brains do the thinking in our sleep and we will revisit it next Tuesday after I explain this one more time. Okay, is that okay with everyone? Let's try again and then let's end class.
Boleh, boleh.
Okay. Okay. Oh, nak habis kelas kan? Okay, same here, saya pun penat. Okay. Let me try to explain this again. Okay, so we have our circuit here. Okay, our circuit consists of VM signal. Okay, remember this is a source. This is also a source. Two voltages in series will give you VM plus VC. This is in series. Kan? Okay. This is what enters the diode. Okay, to represent this before it enters the diode, this is what the symbol is used. This is the symbol used. So this is your VM, okay, your source, your first source, your second source, your VC. Both of these are connected in series, therefore the voltages are added together using a summer. In the block diagram, in your circuit, it's just in series. Okay, so we know this, VC plus VM.
Doktor, sama tu diode lah. Sama lah.
Bukan, summer is just
Oh no.
summer is just the addition of this because they are
Oh,
in series.
Addition of VM VC lah kan.
VM, VC, betul.
Okay.
Okay. In your circuit, these two are in series. When they are in series, the voltages can be added together. Okay, part 2. Okay. At this point, I'm going to label this part as V in. Okay. VM plus VC is V in. After VM plus VC added together because they are in series, right, is V in. Basically just addition. Summer is just the addition of A plus B. Nothing fancy. It's just a summer. Sum. Addition. Okay. After V in, it passes through diode. Why do I label this as V in? I don't have to. I can just say VM plus VC masuk diode. VM plus VC enters the diode. I can say that as well. But I just want to say it's V in so that it's a single term. So V in enters the diode. Diode is a non-linear device. How do I know this? I mentioned this earlier. Let me find. Okay. Examples of non-linear components. Diodes, biased bipolar transistors, and biased field effect transistors. These are non-linear components. If I use a resistor or linearly biased transistor, ada dua kat sini, transistor. Regular transistor is non-linear. Linearly biased transistor is linear. Okay, what does that mean for our circuit? This guy is just a diode, which means that this is non-linear. What if I put a resistor here? Then I will not get my VAM because VAM condition is it requires the circuit to be non-linear. So if I put a resistor there, goodbye, no more AM signal, nothing gets transmitted. It's just a amplification circuit. We don't want that. So we maintain our diode, which is a non-linear device. Okay, back to this diagram. So we have our V in here. These two are added together and this is called summer. Summer macam tu And then this is V in. V in enters diode. This is our non-linear device, which is very, very important. And then afterwards, we get our V out after the non-linear device. So if I were to draw this, I don't have space, but we will try. VM, summer, VC, or it can be flipped, sama je, it's addition. I have V in as the summation of these two things, passing it through to the non-linear device, let me call it ND, I will get V out. Itu je. That is it. Okay. Now, yes,
ND tu apa tu? ND.
non-linear device.
Apa device?
Non-linear.
Okay, okay. Nalini.
The diode or the non-linear device. It can be a FET. It can be a transistor. In this example, they use a diode. But any non-linear device will work. Okay. Now, our devices that we use in our circuits is not perfect. Yes.
Betul.
Yes.
Kalau pakai resistor, linear tak?
Linear, betul?
Okay.
Okay. Where was I? Apa tadi saya nak cakap? Non-linear device. Apa? Okay, tak apa. V in enters non-linear device, produces V out. So non-linear device is not perfect. Okay, I have established this. Our components that we use in our circuit is not perfect. Therefore, you will get undesirable noise. Undesirable noise because our our device is not perfect. Because in the real world, everything is not perfect, right? Okay. So when it is not perfect, instead of getting this, remember this is our good scenario, the not so good scenario but still workable is this, noise or harmonics. Okay, these are the unrelated stuff that we will get because the device is not perfect. So I don't want this. As an engineer, I want this to be transmitting at the best way possible, the best bandwidth, the best power. I don't want to spend power on this. I don't want to spend bandwidth on these noise. They are not important. So what do? I pass this through a band pass filter. Okay, this is a band pass filter. Okay, band pass. Okay, what does it mean? It means I have a band. Okay, jap. This is, I have a bandwidth that I set this thing to. Band is bandwidth. I pass the signal through a bandwidth and I filter it. I pass the signal through a bandwidth and I filter it. Okay. This is how the current signal looks like. We have the harmonics, right? I pass it through a band pass filter which has a fixed bandwidth. Fixed bandwidth. Okay. I can decide how big this bandwidth is. I can decide. Let me decide what the bandwidth is. I decide, okay, I have some money that I can spend on the bandwidth. It can be a little bit bigger than usual. So instead, I want to make it 300 hertz. So this is my bandwidth for my band pass filter. Okay, let's say FM is 100 hertz. This is an example. FM is 100 hertz. So to get our AM signal, the bandwidth should be 2 FM, right? This is the minimum. So this is going to be 200 hertz. This is the bandwidth minimum for AM signal. But my bandwidth is 300 hertz. How will that look like? So instead of cutting it here, which is 200 hertz, I'm cutting it here. So I have some extra space that I'm passing through. So what happens after it passes through this portion? This part is eliminated. This is why it's called pass. It passes through a certain bandwidth. So this guy gets passed through. Yep.
Sebab dia pendek
But dia pendek. What does pendek mean?
Tak adalah, dia kan macam dia tak sampai lah level bandwidth tu, so dia tak lepas lah.
Oh yes, correct. That is correct. So the bandwidth is narrow. Maybe narrow is the right word for it. The bandwidth is rather narrow so that anything that is outside its range gets suppressed. It only allows this portion inside the bandwidth of the band pass filter to pass through. Okay, that is bandwidth. I fixed it to 300. What else do I need to fix for my band pass filter? I need to fix the resonant frequency.
Doktor,
Yes.
kalau bandwidth tu tak cukup besar, dia tak cukup lah nak ni kan, nak
Okay, that's a
pass.
good question. Betul. That's a good question. Your friend asked, what happens if my bandwidth is less than 200 hertz? Okay, if it is less than 200 hertz, it means that I will cut it here. What I will get is just FC. So you are defeating the purpose of modulating the signal in the first place because you don't get your FM, right? So your bandwidth needs to be really designed properly. Okay, is that okay? So you need the bandwidth of the bandpass filter to be slightly bigger than your AM signal, but not smaller than your AM signal, because otherwise you will only get your carrier. That was the first condition. Fixed bandwidth that is greater than VAM, this guy. Okay. And then the second condition is your resonant frequency should be at FC. So the midpoint of this bandwidth is here. Okay, what if my resonant frequency is not at FC? It is at FC plus FM. What if? Okay, our fixed bandwidth is 300 hertz. Okay, I'm fulfilling this condition, but my resonant frequency is at FC plus FM. What will happen? I will cut through the signal like this. I will get this signal and probably this signal, but I will not get FC. So it still transmits signal, but not the one that we want. You get SSB, but a very confusing SSB because there is an additional thing going on here. Okay, so I'm going to end class here. We will revisit this next week. Okay, have a great weekend, everyone. Take care. Don't forget to study for your quiz. I'll see you next week on Tuesday and Friday. Bye-bye.
Baik, doktor. Thank you.
Thank you, Doctor.
Welcome,
you, Doctor.
Doctor.
Thank you, Doctor.
Welcome. Bye-bye.
Doktor,
Yes.
nak tanya pasal quiz boleh tak?
Boleh?
Soalan quiz tu ada berapa soalan?
Oh, I have not designed it yet, but it will be 1 hour. Maybe 3 questions. I will let you know later.
Okay. Doktor, dia calculation dengan fact soalan dia?
Calculation and
Fact.
facts. Betul.
Okay. Terima kasih, Doktor.
Okay, welcome.